In this video, we will talk about pressure in fluids. We will first introduce the concept of density and move on to pressure in fluids. We will show how to calculate pressure in fluids in terms of net force and surface area. This is followed by a discussion on how a pressure varies with respect to depth within a liquid. Finally, we will solve a few problems to demonstrate these concepts. Let's begin with the density of an object. Density is a scalar, so it has only magnitude. It is defined as mass over volume of an object. Mass of the object over the volume of the object, and we use the symbol rho to define it. Now, as you can see, since mass is measured in the units of kg and volume is measured in the units of cubic meter, the SI unit for density is kg per cubic meter. For example, the density for iron is 7,800 kg per cubic meter, and density for water, fresh water, is 1,000 kg per cubic meter. So as you can see, iron is more dense than water. And another important information that we can derive from the value of density of a material is that how much mass of a material can be contained in 1 cubic meter volume of the material. So in this case, 1 cubic meter of iron has mass of 7,800 kg, or 1 cubic meter of water has mass of 1,000 kg. Let's do a simple exercise. You have a rectangular aluminum block whose mass is 1.8 kg. The dimensions are 5 cm, 15 cm, and 30 cm respectively. So what is the density of aluminum? So as we explained before, density is mass over volume. Now we know what mass is. Mass is given that this block is 1.8 kg. The volume can be obtained by simply multiplying the sides of this rectangular block. Convert it to meter first, so 5 centimeters is 0.05 meter, 15 cm is 0.15 meter, and then 30 cm is 0.3 meter. So when you do the calculation, you obtain 800 kg per cubic meter for the density of aluminum, noting that the denominator here has a dimension of cubic meter. Next, let's define pressure. Let's say you have a surface area A meter squared, and you have a normal force with a magnitude F newtons pushing on this area in the manner shown. Note that the direction of this force is 90 degrees with respect to the plane of the area, hence the term normal force. So we say the normal force is exerting a certain amount of pressure P on this area, and we define that pressure in a following manner: the normal force over that area. Now note, since the force is measured in the units of newtons and area is measured in the units of meters squared, so the unit, the SI unit for pressure, is Newton per meter squared, or you can also express it in the units of Pascal, abbreviation PA. So 1 Newton per meter squared equals 1 Pascal. So an atmospheric pressure, average value for the atmospheric pressure at the sea level, is 1.013 times 10 to the power 5 Pascal, or Newton per meter squared. So these are SI units that we use to quantify pressure, and sometimes we can use a non-SI unit to quantify atmospheric pressure. And since this is the value of atmospheric pressure in Pascal, an alternative unit to quantify atmospheric pressure, or any pressure, is atm. So 1 atm is 1 atmospheric pressure given by this value in pascals, or in Newton per meter squared. Let's do a simple exercise. A room floor with dimensions 5 times 6 meters, 5 by 6 meters, exposed to atmospheric pressure. What is the total force on the floor? Now, since we know pressure is force per unit area, we can solve for the force by taking the pressure given and multiplying it with the area. Now, since this is an atmospheric pressure, let's do the calculation in SI unit. It's going to be 1.013 times 10 to the power 5 Pascal, or Newton per meter squared, and times the area, which is 5 times 6 meter squared, and that's going to give you a value of 3 times 10 to the power 6 newtons for the total force on the floor. Next, let's look how pressure varies with depth. Say you have a pond that is exposed to atmospheric pressure. Let's say the atmospheric pressure is P naught. And we will carve out a sample of water in the following way. It's in a rectangular block form. So the top surface area is A, the bottom surface area is A. Let's take this length here as H. Of course, we are assuming that the entire liquid in the pond is at rest, so this sample is in static equilibrium as well. Now, there are 3 forces acting on this sample. The first force is the downward force that is due to the water pressure pushing on the top surface. Let's call it F1. The second force is the upward force there, F2, that is due to the water pressure pushing on the bottom surface. And then the third force is the weight of this water column, mg. So since all the forces are balanced because of equilibrium, the upward force F2 must be the same as the sum of all the downward forces, F1 plus mg. Now, since we know force can be related to pressure, such normal forces can be related to pressure, the normal force F2 is quite simply the pressure at the bottom surface, P2, times the surface area of that bottom surface, which is A. Likewise, F1 equals the pressure at the top surface, let's call it P1, times the surface area of that surface, plus mass is quite simply the density of the liquid times the volume of this rectangular water sample. And that is given by surface area times H and multiplying finally by G. Now you notice that all the A's will get cancelled, leaving us with the following final equation. P2 equals P1 plus rho G H. What this equation says, the pressure here is greater than the pressure there. So P2 is greater than P1. The difference is this rho GH. Rho GH is the pressure due to this entire water column. So if we assume that the top surface now is exposed to atmospheric pressure, as shown in this later figure, then P1 quite simply becomes P naught, where P naught is the atmospheric pressure. And the pressure P2 at depth H now becomes the atmospheric pressure plus rho GH. So P2 is called the total pressure at that depth, and the term rho GH is called the gauge pressure. So if in a problem you are asked to compute gauge pressure, just compute the difference. If you want to determine the total pressure, add atmospheric pressure to it. So an important conclusion of this analysis is that the pressure increases with depth. Let's do a problem. A home window has dimensions 3 by 2. So let's say this is 3 meters and that is 2 meters. During a stormy weather, the outside air pressure, so outside is here, drops to 0.0 0.94 ADM. So the pressure there is 0.94 ADM. Remember, ADM is not the SI unit, but we can convert that to Pascal if we have to. And the inside pressure, so this is inside, the pressure is 1 ADM. It is just the atmospheric pressure. Find the net force that pushes out on the window. The force on the internal side of the window is going to go like that. So let's call it Fi. The force on the outside of the window is going to go like that, all in 90-degree direction. So let's call that Fo. Now the net force is defined as Fi minus Fo. Fi is the pressure inside times the surface area, which we can calculate. Fo is the pressure outside, let's call it Po, which we know, 0.94 ADM times the surface area. Now, if we factor out the area, we simply get Pi minus Po. Now, what is Pi minus Po? It's 1 ADM minus 0.94 ADM, which is 0.06 ADM. Now we need to convert it to Pascal by multiplying it by 1.013 times 10 to the power 5. Remember the conversion, 1 ADM is 1.013 times 10 to the power 5 Pascal. That is the conversion. A is 6 meters squared, 3 times 2 that is. And when you do this multiplication, you get the net force as 36,500 newtons. And that solves the problem. Problem 2. Calculate the water pressure at a depth of 12 kilometers. Assume that the density of seawater is 1024 kg per cubic meter. So that is the depth at which we want to calculate the pressure. Now this surface is exposed to atmospheric pressure, so we have to take that into consideration. Now we want to calculate the total pressure. So the total pressure equals the atmospheric pressure, that is here, plus the pressure contributed by that much water column, and that is given by the density of seawater, gravitational acceleration times that h. Let's do the calculation in SI unit. So the atmospheric pressure is 1.013 times 10 to the power 5 Pascal, plus the density of seawater is 1024, that's given. G is 9.81. H is 12 kilometers, so that is 12,000 meters. When you do the sum, you will get the following for the total pressure at that depth. 121 times 10 to the power 6 pascals, which is equivalent to 1,280 m. So you can take this answer and divide that by the atmospheric pressure to get this answer. What that shows you is the pressure here is 1,200 times bigger than the pressure there. Problem 3. A container contains 0.18 meter layer of oil floating on water. So this is the oil layer and this is the water layer. And the water layer is 0.3 meter deep. The density of oil is 600 kg per cubic meter. Calculate the gauge pressure at the water-oil interface. That means here. And also the gauge pressure here. So gauge pressure means we don't have to worry about the atmospheric pressure. So that is not needed. So the pressure there is simple. The gauge pressure is given by the density of oil times gravity times 0.18 meters. And when you do the sum, you will get 1,059 Pascal. Keep in mind, density of oil is 600, G is 9.81. Gauge pressure here is the pressure due to this column plus the pressure due to that column. The pressure due to this column has been calculated, 1059. Now the pressure due to the water column is the density of water, which is 1,000. 9.81 is G, and the length of the column is 0.3. And that's going to give you 4,002 pascals. And that solves the problem. Thanks for watching.